Well, welcome back to our course on system engineering. We're now continuing in our third section that talks about some more supplemental topics on system engineering. We talked about graphical modeling techniques in our last lecture, leveraging a little bit on things that we have talked about with graph theory, but quite more extensive. And it gets into various things that are done with model-based system engineering tools. And now with this lecture, we're going to be talking about the decision analysis for design trades and some of the tools and techniques, how that would work. And we'll actually walk through a couple examples so that you can see how that would actually be utilized. So this chapter presents the key topics of decision analysis as an integrative way of supporting the many decisions that are part of the design and integration of a system. These decision analytic topics include the development and qualification of the values. So we have objectives, value functions and trade-offs, and modeling of uncertainty regarding facts. So interesting things for us to consider. Well, let's, as we've done before, use some relevant definitions that may help us in this process. And first, for this decision, this is an irrevocable allocation of scarce resources. So therefore, you want to make good decisions. Decision analysis is the conversation with the decision maker, what the decision maker, the stakeholder in the system engineering cares about. So that's getting into values, what the decision maker can do, discussing the alternatives, and what the decision maker knows, the facts or absence thereof. And if there's not as many facts as one might know about the unknowns, then there's going to have to be a more conservative type of a design. So you can see how that's going to impact things. In terms of axioms of decision analysis, there's the order rule, the equivalence rule, the substitution rule, and the choice rule. For the order rule, the outcomes associated with design alternatives can be ordered from least preferred to most preferred on each objective and fundamental objective hierarchy. An equivalence rule is, say you have three outputs, A, B, and C, where A is preferred to, that is greater than B, and B is greater than C. Therefore, there's a probability of P of obtaining outcome A and a probability of 1 minus P of obtaining C that makes us indifferent to obtaining outcome B. So this gives us a way of how to relate these different possible outcomes. A substitution rule, you can substitute any combination of outcomes in a decision-making situation if indifferent between them. So they're basically equivalent in the context of what you're looking at. And finally, the choice rule is for two alternatives with the same outcomes and same probabilities of outcomes. If one of the alternatives has a higher probability associated with it than the outcome, it is preferred, then choose this alternative. So you can make a real choice, is what we're getting at. So we'll get into more details here for the order rule. So one preference over aggregated across all objectives, there is a single list of outcomes ordered by our preferences. It is impossibly indifferent between two outcomes on a specific object. Our preference rule order does not need to be the same from one object to the next. In fact, there would be no need to have multiple objectives if this were the case. The order list must be transitive. That is to say that any outcome can only appear once on any ordered list. And so this then talks about, well, if this is not the case, we become the subject of a money pump, and we give an interesting article analogy with cars of how you could, if you like this more than that, like that more than this, then you could end up having some circular type of rationale, and that wouldn't work. So for axiom of results, normative theory of decision-making results indicates that the maximization of expected utility. So we want to be looking at the utility for various alternatives and then evaluate them. So utility is measured in an interval. The interval scale preserves equal intervals of measures and can be multiplied or divided by a constant and have a constant added or subtracted from it. a ratio scale of measurement for utility could be used, but is not necessary. The probabilities are constructed on a ratio scale. So we're trying to evaluate the utility of something and come up with some general constructs of what that actually might mean. I think as we get into examples, this will become clear. What about multi-attribute value analysis? And so quantitative methods for aggregating a stakeholder's preferences over conflicting objectives. So you can have some weighting factors for each of these objectives, and then you can have like a simple addition of those based on the different weights and the different values for each one. So value, and so we want to be defining the objectives of interest for a system. So we talked about that already, and you want to consider the value scale for each object. So what would be more important than another? And working with a stakeholder, this would be a fairly straightforward thing to do. And then you are going to have, as a result, of value weights that address the relative value associated with improving from the bottom of the value scale to the top. And so then we'll see how that starts to flesh out. So what are properties of a value function and weight? Value functions is an interval scale. So you can be thinking, what is something that's relevant to what you're trying to get at? So maybe a temperature. You would say, if you're thinking of your soda machine example, you would want to have the sodas maintained within a certain range of temperatures, and how closely can it stay to that optimal temperature. Weights are on a ratio scale. It can arbitrarily fix one point and then reflect swing in value from a high to low. And so maybe you have a redesign, and so you have an idea that has to be as a minimum what you had previous. And so you would like to maybe have it fixed by that previous performance value. Well, these next two charts are notional. This is actually sort of a generalization of an analysis of alternatives that I did for a paper, and that reflected the results of analysis that I did. And so maybe you can be thinking of this in a couple of areas. First, we have here, we're showing 6 alternatives. There's a scale that we can have for each of these criteria, so you can actually weight it to some level. And maybe you have some subtle differences in a submission area and in terms of approaches. And so we're showing some 2 possibilities that could apply to mission area 1, 3 that would apply to mission area 2, and 2 that apply to mission area 3. So we're all in the same ballpark, but we're getting a little bit more into some of the specifics. And then we have a handful of criteria. And so as a result, we can have the scale, we have the scale. And then if we were going to weight them, then we could start to have these impacting what we would get in terms of these results. For this, we're not talking about having this additional feature of weighting. It's just a simple scoring of a handful of criteria. And then we can show the, here is just a listing of possible types of criterias that might be relevant. And you can see how this last option number 6 scores the highest. There's still some relatively close scores of these, and then it starts to fall off for some of these other ones. So the difference between what I'm showing in these 2 slides and what is talked about here with this weights is, if we had weighting, we would have yet another column. And so we would have what would be the scale, and then you have a multiplying factor by a weight, and then it would start to impact these scores. So the next handful of charts will give a little bit more thought into how we can be deriving what these values would be and the value functions. Is it going to be linear? Is it going to be exponential or logarithmic? And so here we're just seeing some different types of curves that could be things that could be used: exponential, logarithmic, linear, or an S-curve. Sometimes an S-curve is something that's quite useful. So it tends to have a linear approach towards the middle, and then it starts to level off at both at the low and the high end, as we're showing with those examples. So here is an example of a linear value. So if it's a relationship, a linear relationship between the input and the output, or an inverse relationship, we would be seeing that. If you have a concave, and so there's a diminishing return as you go up the scale, or you could have a various ways of how you can have a concave type of a value function. You could have a convex, and so there is an increasing return as the further up you go up in the scale. And so that gives an implication of what you would want to be choosing for that type of a factor. So there are various curve elicitation methods. And so you can be thinking about that, whether say something like a difference standard or a bisection. And here is a different standard sequence. And so here we're talking about consecutive days of vacation. And here we're showing the value that might be related towards that is one way to be thinking about it. So for bisection, so here, please set level B so that the change from level A to level B has the same importance as the change from B to C. So we're cutting it in half, and we want to be seeing how we go from 50 to 110. So basically, we just cut it in the middle. So B would be at 80. So that would be bisection. Swing weights, if we are going to be using this, it must reflect the relative value associated with the increasing from the bottom to the top of each scale value. In terms of weight elicitation methods, you can have direct or indirect. For direct, you can say spread 100 points. You could anchor on the least or the most important, or have an approximation based upon ranks. Indirect, you can be using some analytical hierarchy process, a balance beam, and we'll talk about that a little bit here, a trade-off, maybe doing a pricing out or a graphical bar adjustment. So basically, there's a variety of ways of how you can determine what would be the best weighting scheme that you would want to be doing, and changing the weights is going to start to skew things a little bit, but maybe that's exactly what you might want, or you may need to get greater precision because all of the potential outcomes are very close. And so that could be another motivation of why you'd want to adjust the weightings. So here is something called an analytical hierarchy process. And so we're turning to the example of a design trade-offs for a communication system. Suppose that the stakeholders provide the judgments shown in the table below into the analytical hierarchy process. And so basically, they're starting to give you a relationship between some of these requirements: throughput, availability, operating lifetime, process cost, and operating costs. And so here we can start to be using this information to impact what we're going to be doing with our weighting scheme. So here is an example of a weighting scheme. And so how, so we have these different criteria. And so A, from this, you can see it's more important than B and C, but if you stick D on that, all of a sudden that's going to be, give more of an impact of that aggregation than with A. So A is important. It's more important than 2, but not more important than 3 in a general sense by looking at that. So that's a pictorial view of the balance beam example. And so using the balance beam approach for a communication system design, the stakeholders are asked to compare the swing and benefit of the throughput to that of the combination of the swings of availability and the operating life. And so the stakeholder respond to the combination is greater than that of throughput. And I'm not going to read through all of this, but this just gives you an idea of how you could finally boil it down to weights as a result of going through this process. So what's the implication for value analysis? Assessing quantitative judgments. You can be utilizing formative learning experience, not a reporting experience. It enables experts to create inconsistencies to learn from and form sound opinions. So you can be starting to get some greater insight into sensitivity analysis. You can be asked for a redundant judgment, use multiple formats, and seek multiple perspectives. And so how do you get better context, and how can you improve your decision-making by using a variety of different approaches? And so that's what we're getting at. Okay, for probability theory, I'm not going to really go over this. Bayes' rule is something that is used quite a lot. And you would, are the weights and the criteria that you're using, are they independent? And so here's the equation for probabilistic independence. And you would want all of the elements to add up to the total probability. And so we have an equation for that. And then, of course, we mentioned briefly Bayes' rule, which is something that's used often. Relevance diagrams are a directed graph or digraph that is a statement of the joint probability distributions among the set of random variables as a factorization of conditional and marginal probability distributions. Cannot have a cycle, and the arc between two nodes cannot be flipped. And so you might remember a cycle when we were talking about graph theory. And so a cycle is it's a closed loop. And so here are some sample relevance diagrams. So independence, there is no connection. There's a relevance, and so you draw an arrow to that. And a flipped arc means that you would be going in the opposite direction. So that's what we're showing by that reversed arrow there. So here's a notional relevance diagram for the elevator design. And so here we have the control technology, and we have the elevator performance, availability, and cost. And then we have power technology feeds into availability and cost. So that's the first diagram that we have. And then we can be throwing in this additional thing, and we can survey the results on power technology. So we're including the survey data on power tech there. So here is we'll talk a little bit about decision trees and influence diagrams. And so for nodes, we have the syntax for boxes are decision nodes with alternatives, ovals are chance nodes with outcome states, triangle round tangles are value nodes, and double oval round tangles are deterministic value nodes. And we'll see some examples in the following slides. For decision trees, it shows a chronological like sequence of the nodes. The tree expands exponentially with nodes, and alternatives / slates with probabilities are shown. For influence diagrams, it shows a probabilistic information and functional relevance between pairs of nodes. Node chronology, alternative states, and probabilities are shown, and it expands linearly with nodes. So we have nodes, decision trees, and influence diagrams that we're going to be exploring. So here is a sample decision tree and an influence tree. So we can start to see how this gets to be a larger number of nodes as we work our way through this tree. And we also see an influence diagram as we're trying to figure out if we want to do a build or buy trade in this other diagram. Here's a relevance diagram that shows the relevance meaning of arcs. And so we go from a decision. So we have a probabilistic relevance to going to chance. And you can walk your way through this just as easily as I can. So this is just giving a nice synopsis of the relevance meanings of arcs. Here's a sample influence diagram for requirements allocation. And so I'll just leave that up to you. You can look that over and read the text to get some more context for that. So Now we get into an example where we're starting to pool some of these together in a couple different ways. And here's a summary of the requirements allocation case study. And so here we have a couple different things. We have performance, life cycle cost, and availability. And we have the weights that are assigned for each one of those. And so we can be in the operational architecture, we can be looking at control, power, and risk. And for power, we can be looking then at control and power for the performance allocations, moving down to availability allocations, and then finally cost allocations. So this is something that might end up being useful. We also have some technology uncertainty about the controller technology and the power technologies. And so those are just a few things to be contemplating as we're getting through this analysis process. Let's have some definitions. First of all, for risk, this is the exposure to the chance of loss. And so that's a dictionary meaning. Risk can be thought of as a combination of the probabilities of an event occurring and the significance of the consequence of that event occurring. For risk management, it's various processes used to manage risk. So there's risk avoidance, risk transference, risk management, and risk analysis. So risk avoidance is the selection of a low risk alternative. Risk transference involves options that transfer risk to others. So how can you start to re-wicker how things are being done so you have risk transference to an area where it's lower risk? You have risk management involves the use of hedging strategies. And so there are some risks that you can't avoid. And so you need to be prepared that if this happens, you're ready for it and you can minimize the things that can happen. So you come up with a mitigation strategy. Finally, risk analysis addresses risk explicitly where decisions are made in uncertain situations. We then here are getting into expected value versus utility. And so premium risk equals expected value minus certain equivalent. And so here we're just seeing some examples of how that might be playing out. Here we're showing two types of queries for risk preference. I'm just going to skip over this for now, and you can be looking this over at in the textbook. In addition to this, talking about zero effect. And assessment queries for risk preference functions. So once again, I'm not going to just talk about this for the sake of trying to focus on certain things within this material. For exponential risk preference function, here we can see an example how that might look, where we're deriving a risk preference function, and so we're laying that out here. We have delta properties. A delta property is an increase in all outcomes of the lot. So as an example, an increase in all outcomes of the lottery by a constant amount delta results in an increase of the certain equivalence by the same amount delta. So one very important implication of the delta property is that the buying and selling prices of a lottery are the same. So if you buy a lot, you buy a little, it's still the same kind of relationships in terms of the probability of getting an outcome. For risk tolerance is the inverse of the risk aversion coefficient. So there's a quick and dirty method for assessing a decision maker's risk aversion coefficient for an exponential function, the value of R for which the decision maker is indifferent to accepting the lottery. And then we'll get into the specific example talking about a lottery. So I'm just going to skip that and just focus on just giving a thought or two on risk tolerance. Okay, well now let's talk about an examples system And so this was the requirements development for the US Marine Corps Mobile Protected Weapons Station. The Marine Corps needed a mobile assault scout vehicle in the early 80s. Value curves developed with a user as guidance for industry, so they had that. They developed weighted values. They varied by scenario, and ranges were put in the request for proposal. And then Congress forced the Marine Corps and the Army to purchase an off-the-shelf vehicle. So they were going to have to work together on this. So there were several operational concepts that had to be thought about. And so there was an offensive role, defensive role, and subsequent operations. And so these were the things that had to be considered. So offensive would be assault support with the infantry. Defense role would be, say, like having a blocking position. And finally, for subsequent operations, the system would be employed with a combined arms task force. It would no longer be in an amphibious assault role. Blue forces are task organized, and there would be most likely be low to medium intensity non-nuclear conflict. So there's more details on this chart that I'm not reading, but just giving you a little bit of perspective. These were the operational concept modes that had to be considered, 3 different scenarios. So, and here is an IDEF 0 diagram showing the external systems diagram. I won't go into that in detail. And so here are the performance requirements. You have the operational effectiveness. You have the assault support, the blocking position, and the subsequent operation goals. And so there were a couple main things that were considered in the performance requirement region. So for the performance requirement and the assault support, so there was a goal for having a certain level of firepower, having the ability for helicopter transport, mobility, and other things. And so these are just being laid out for how that could work for the assault support. You have the more details for the firepower, the accuracy, the lethality, and other types of measures that were fleshed out in terms of the requirement. Then you have the lethality against a goal, and so various types of targets that could be considered as possible goals that they would be considering. Mobility, how fast can it go across different types of terrain, cruising range, the road speed, and how could it operate in water. Then we have some curves for different things. And so here is a utility function for the helicopter transport. So you can see that there's an inverse relationship that as the tonnage of the transport goes up, it's going to get harder and harder for it to be able to be transported by helicopter. For tank lethality, you can see that there's an S-curve approach for capturing that. And so we're seeing the types of curves that we have, and they're not all always the same for each one of these types of parameters for target acquisition in bad weather. And so we have different types of smoke and versus, so there would be some type of issues with these types of weather problems, and then having a clear night, it's clearly going to have the most best performance. So the mobility in terms of percent terrain not negotiated. And so here is just another utility curve that we're showing that being laid out. Mobility in water. So, and then we want to be establishing a weight trade-off for each of these areas. And so here are the various elements where we're starting to aggregate them up. And so this is a little bit notional where we're not going through all the details, but we can see we're getting an overall type of score as a result of these various types of parameters of requirements and having weights that we could be using for each type of option. So for the overall results, the ranking for this vehicle for in terms of the operational effectiveness goal. And so it does quite well for the quick and fast, high survivable, it does okay. Having a big gun, it has a utility score that's not quite as high as the other factors. And then we have the sensitivity factor. And this can be important because maybe you might want to be tweaking this design point a little bit based on things that you start to uncover as you continue to work out the analysis and leading into the design and the acquisition. Here is a picture that shows the dynamic sensitivity analysis for different types of parameters. And so this isn't active here as a stale, but you could actually, if you wanted to start to push back and forth the weights, you can see how things would end up being adjusted for these big elements here, the big gun, the survivability, and being quick and fast. Here we saw an example of one type of relationship between those three main elements. Now we could start to flesh this out for and vary these a little bit. So we have these various types of weights, and we had a diagram here that was showing the weight trade-off for this one example, but you can modulate this a little bit and then see what would be the impact if we were to update those based on some other criteria. So now we have a graph of an alternative. And so we're starting to show an aggregation of these things in terms of firepower, mobility, survivability, helicopter transport, and reliability, availability, and maintenance. And so here we're seeing that for a specific scenario being fleshed out. And so does that perform well enough to meet the requirements of both the Marine Corps and the Army for them to go forward with that option? So here is an alternative comparison chart. So you can be seeing this, say you comparing one to another. And so maybe with this one option that we can see it does well in a variety of things. And so we're seeing the blue, but that comes at a cost of not doing so well on other areas. So just to conclude, we're seeing examples of how the work that we do and decision analysis can be useful for design trades and ultimately coming up with a design that we want to be going forth with. So thank you very much. That's going to end it for this lecture.